Good morning, everybody from the greater New York area, I'll say, which for me means New Jersey. Thanks very much to Alex for organizing all of this. It's been lovely so far. We're now halfway through, I guess, and so we're about to start the second half. So thanks very much for including us. And I do want to say, once things get back to normal and people start traveling again, we'd love to have you visit our seminar, so let us know if you're in the area. So, but without any further ado, let me introduce my friend and colleague, Deepak Bal, who will be talking about size Ramsey numbers of paths and cycles.
All right, thank you for the introduction and for the invitation. Welcome to New York. So now I guess you need pizza and bagels instead of wine and cheese, but that'll do. So I'm going to talk about size Ramsey numbers of paths and cycles. And this is based on joint works with Louis DeBiasio from Miami University and a student of mine, Ellie Schudrich, or a former student at Montclair State. Okay, so I'll start with the definition of the ordinary two-color Ramsey number. So we say that G arrows H if every two coloring of the edges of G contains a monochromatic copy of H, and the two-color Ramsey number is the smallest integer n such that the complete graph on n vertices arrows H. So some classic results, which probably most people here know, that the Ramsey number of K3 is 6 and K4 is 18. And these bounds on the Ramsey number of a general complete graph KT have stood for a long time, at least up to the base of the exponents, √2 and 4. So one of the topics of this talk is about paths. So what about the Ramsey number of the path Pn? Well, so for us, Pn is the path on n vertices. A theorem by Geringer and Garfasch says that essentially the Ramsey number of Pn is 3/2 n. So this coloring shown here shows you the lower bound. If you take a complete graph on just under 3/2 n vertices, then and you color it like this, then you can't have a red Pn because there's not enough vertices here. And this blue bipartite graph also, you won't be able to get a blue one either. Okay, so we could think of the Ramsey number R of H as answering the question, what is the least number of vertices in a graph G such that G arrows H? And when you phrase it like this, then you might as well always take the graph G to be the complete graph. Right? So, but what happens if we replace the word vertices with edges? So that brings us to the concept of the size Ramsey number, which I'll be talking about today. So the two-color size Ramsey number of a graph H is the smallest m for which there exists a graph G with m edges such that G arrows H. Okay, so I'll just tell you how does one prove upper and lower bounds on a size Ramsey number? Well, to prove an upper bound of m, your job is to show that there exists a graph G with m edges which arrows H. So you kind of have two jobs. You have to find a graph with m edges, and then you have to prove that that graph arrows H. And to show a lower bound of m, you have to show that every graph with m edges does not arrow H. So in other words, for any graph on m edges, you have to find a two coloring which does not contain a monochromatic H. And I'll just give a little warning here, which is, I think, something which confuses people, and which is that there's no assumption on the number of vertices in G here. So when you're searching for these graphs on M edges, you're not saying anything about how many vertices they might have. Okay. So some simple observations. The size Ramsey number of H is, well, it's at most the ordinary Ramsey number, choose 2. And why is that? Because the complete graph on the ordinary Ramsey number of vertices definitely arrows H by definition, and that graph has R of H choose 2 many edges. So that's always an upper bound on the size Ramsey number. And in fact, Erdős, Fodry, Rousseau, and Schelp proved that for complete graphs, the size Ramsey number is exactly that upper bound. Okay. So, what about paths? Well, this upper bound that I mentioned here, the ordinary Ramsey number of Pn is essentially 3n over 2, and 3n over 2 choose 2 is on the order of n squared. So the upper bound you get here is basically n squared. Okay. So the Erdős, Fodry, Rousseau, and Schelp actually asked if perhaps this size Ramsey number is smaller than n squared, maybe even linear. And Erdős listed this among the combinatorial problems which I would most like to see solved, and offered $100 for the solution of this problem. So, okay. Again, so how does one prove upper bounds on the size Ramsey number? What we need to do is show the existence of a graph with the least possible number of edges, which arrows Pn. So the solution to the problem came from Beck in '83, who proved that this is upper bounded by 900n. So it is indeed subquadratic, and it's in fact linear. So in other words, remember what this means is that there exists a graph with 900n edges, such that no matter how you two-color the edges, you get a copy of Pn. And then there were some improvements on this along the way, including a deterministic construction. And so the bounds have come down here, and finally the best known upper bound is 74n due to Dudek and Pralat. And how do they do it? Basically, they use a lemma that essentially says that if a graph has no large bipartite holes, then it arrows Pn. So what is a bipartite hole? It's two vertices with, or two sets of vertices with no edges between them. So if a graph has no large bipartite holes, whatever that means, then it arrows Pn. And they showed that a random 27 regular graph on 5.4806n vertices satisfies this for the appropriate definition of large. And this has 74n vertices. So notice again that, you know, the graph that they find which arrows G has some other, you know, we don't know how many vertices it'll have off the bat, but some optimization landed on this number of vertices in their construction. Okay. All right, so to show that a lower bound, what do you need to show? To show that the size Ramsey number of Pn is greater than m, you need to show that every graph with m edges can be two-colored in such a way that there are no monochromatic paths. All right, so a trivial lower bound. Okay, so I'm going to show this chart here. This axis is C, and I'm giving lower bounds of C times n. So why is 2 a trivial lower bound here, because basically if G has 2n minus 4 edges, then what could I do? I could color n minus 2 of them red and n minus 2 of them blue. And since Pn, the path on n vertices, has n minus 1 edges, I'm definitely not going to get a monochromatic Pn, right? Definitely no monochromatic Pn. Okay. So that's the trivial lower bound. Beck proved that you can actually get 2.25n in 83. And then in Bolobosh's paper, it was proved that you can get 1 plus square root of 2 times n, which is around 2.4n. And then Dudek and Pralat proved that you can get 2.5n. And this brings us to our result, which I want to tell you about, which is that you can get 3.75n. Now, putting it on this scale is basically the way I had to convince you that this is even a result worth mentioning, because the gap between these two things is bigger than it was before. So, and also I'm only saying this to point out that when you first hear this problem, you might think that it wouldn't be so hard to move away from 2n, right? You wouldn't think it would be too challenging to get something much bigger than 2, but we tried and we got 3.75. And so I think that it's kind of a challenge to the audience. I think there's definitely room for improvement here. As far as what do people think the answer is, the only thing we could really find is this quote by Bolobosh, which says, "It would not be surprising if r hat of Pn turned out to be about 8n." So I don't know. I'm not sure what exactly the intuition was behind that statement, but I think maybe it's a pretty specific number to say, but I trust Bolobosh. So okay. So what do I want to tell you about this? I'll tell you the basics of the proof idea. Okay, so I'm going to make, again, remember, I'm trying to color a graph with 3.75n edges and avoid a Pn. So, and also, I don't know how many vertices the graph is going to have. So I'm going to call that number of vertices capital N. And so let's suppose that G is a graph on capital N many vertices and that it has bounded degree. That's another assumption we'll have to deal with. Then basically we have there's a lemma that says there exists a partition of V of G in the sets of size at most square root of n, such that the number of edges inside the sets is at least asymptotically n. So essentially, how does this work? Well, since G has bounded degree, what you can do here is take a spanning tree and kind of cut it up in the appropriate places in order to get these sets of size at most root n, where there's basically capital N many edges inside the sets. Okay. Then what? Then you take these sets and you randomly partition them such that each part of the partition has less than n vertices. And you color the edges inside the parts. So you randomly partition them, say, you color the edges inside with blue and you color the edges across with red. Now, if you did this in such a way that the number of vertices in each of these parts is less than n, then you're definitely not going to have a blue Pn. And then, well, if the number of red edges going across is less than little n minus 1, if this is less than little n minus 1, then there's no red Pn either. So that's the whole basis of the argument. Okay, so let me a little more detail. This is the lemma that if so again, you have to kind of split on cases based on how many vertices the graph G has. But if it has less than 2n vertices, then you can find a bipartition of G into sets of size less than n minus 1, such that the number of edges crossing the partition is at most this here. So this, by the way, if this minus n, big N wasn't here, then this is what you would get if you just kind of randomly partition the vertices into a sets of size, well, you let it be in the left with probability alpha, and you let it be in the right with probability 1 minus alpha. So you would get this many edges crossing the partition, right? But the result I told you about over here, the fact that you can capture about n edges inside of these small sets, that guarantees that those n edges will land within the parts, within the left and right hand parts, right? So that gives you kind of this savings of minus n here. And essentially you're good if the number of edges crossing the partition is less than n minus 1, then you're good. Then you won't have a red Pn. And similarly, there's, again, we don't know how many edges or how many vertices the graph G will have, but if it has between basically 2n and 3n vertices, then you can tripartition the vertices into sets of size less than n minus 1. So the number of edges crossing is like this. And if you kind of rearrange this and see what this condition gives you, then you get a picture which looks like this. The axis here is basically, if this axis is, say, C, then what we're looking at here is the bound you get based on the number of vertices. So over on the left here, it's graphs with 1.5 little n vertices up to graphs with 3n vertices. And what bound do you get using this argument? That's shown here. So if you just do this, then you get a lower bound of 3.732n. And so the min happens somewhere in here. But the result I mentioned was 3.75. So how do you do that? Basically, the bottleneck occurs when G is close to 3n over 2. So in that area, when n is between 3n over 2 and 5/3 n, basically you can use a different type of coloring. You can modify the Ramsey, the ordinary Ramsey coloring, and kind of get a different bound there, which improves as n gets closer and closer to 1.5 little n. And so then the bottleneck is right here at, so the basically in our argument, the place to look to start improving is when capital N is around 5/3 n. That's when our separate argument doesn't, or stops working, and we have to rely on this lemma to do it. Okay, so that's what I wanted to say about this size Ramsey number. I mean, I think that the lower bound just hasn't received that much attention, and I found it to be a pretty interesting problem. So that's why we decided to look at it. And it's related to these, bisection width and min cut type problems. So it'd be things you can apply there. Okay, so next thing I want to talk about is what happens when there's more colors and what happens in hypergraphs. So we say that G S arrows H if every S coloring of the edges of G contains a monochromatic copy of H. And the S color size Ramsey number is the smallest M for which there exists a graph G with M edges that S arrows H. So now it's just the S color version. And also we can define this for hypergraph. I put that in there. Okay, so for upper bounds for the S color version, so Dudek and Prahlad also proved that the S color version is linear in N, and they got an upper bound depending on the term depending on S was exponential in S. So this is basically taking their random graph argument and using that lemma about bipartite holes and just applying it inductively. But then Krivulevich proved that it's actually, you can get an upper bound of S squared log S times N. And then Dudek and Prahlad gave an alternate proof of that. Okay, so that's much better than 4 to the S, the dependence on S here. All right. The lower bounds, well, it was also proved that, so the upper bounds are like S squared log S times N. And the lower bounds are actually, it's at least on the order of S squared times N. The dependence on the number of colors is at least S squared. So here's one way to see this. You can lower bound the size Ramsey number, the S color size Ramsey number of Pn by 1/2 S plus 1 times the ordinary Ramsey number of Pn minus 2. Okay, so how does that work? And then this, there's a lower bound on this of basically S minus 1 times N. And so this gives you a lower bound of S squared N. Okay, but why is this inequality true? So what you can do is, suppose you have a graph and it has less than this number of edges. Then let L be the set of low degree vertices. You got your low degree vertices and then you've got the rest. And well, the degree condition on, by low degree vertices, I mean vertices of degree less than or equal to S, where S is the number of colors. Well, then this assumption gives you a bound on the number of vertices in V minus L. You know, just by rearranging this, then you get that V minus L is of size at most the ordinary Ramsey number of Pn minus 2. So no matter what the edges look like inside of here, you know there's no monochromatic. One can color the graph induced on G, the graph induced on V minus L, so there's no monochromatic Pn minus 2. And then you can take the vertices in L and just kind of order them arbitrarily and color them in such a way that the forward edges and the edges to L, so what do I mean by that? Forward edges meaning edges going forward within L and edges going to here, all receive distinct colors. And what does that get you? Well, basically by the way that you colored this, you're not going to get any long paths within L, and also you won't be able to extend any path in V minus L by more than 2 vertices. Right? At best, you could extend a path down here at its endpoints, but you won't be able to say, take 2 long paths down here and connect them via L, by the way that this was called. Okay, so I'll point that out because it'll kind of come up later, the way that you can, this lower bound. Okay, so What about hypergraphs? So the study of hypergraph size Ramsey numbers was initiated by Dudek, Lafleur, Mubai, and Rodel in 2017. And well, they talked about all sorts of problems, but I'm going to concentrate on K-uniform tight pads on n vertices, and I'll denote those with P, N, K. So remember, this means K-uniform and n vertices, and tight means k minus 1 overlapping. So consecutive edges in the pads overlap in k minus 1 edges. So this is a 3 uniform tight path on 6 vertices. So this would be Pn P6. Okay, so these authors ask whether the size Ramsey number of Pnk is linear in n when k is fixed. And essentially this has been proved now. So for 3 uniform tight pads with 2 colors, this was proved in 2019 by Han, Kohayakawa, Letzter, Mota, and Parchik. And then the whole problem for S colors and all K uniform was solved very recently by Letzter, Prokofsky, and Yepremian. And so actually in this paper, they do a lot more. They do things with bounded degree trees and powers of bounded degree trees and show that all those things are linear in n. But hidden in here, there's some constant, or there's some dependence on K and S, and if you're taking powers, then the power T, and one might ask, so what are the dependents on those parameters, even though this is linear in n? So that's something we might look at in terms of lower bounds. So the only thing we've seen very recently, Winter proved the following for 2 colors, that in 3 uniform tight pads on n vertices, he can prove that the size Ramsey number of these is at least 8/3 n. And in general, for 2 colors and K uniform tight pads, he proves that you can get a bound of essentially log base 2k times n. So the dependence on k here is like log in this lower bound. Okay, so what did we do? We started looking at this for more colors, and we have a few results here. So one result we can get is essentially this is exactly the result back here, which I showed you kind of the proof of. It's this, but for hypergraphs. So that's not so surprising. You can do the same argument here and look at vertices of degree less than s, and a similar argument works to get this lower bound. But then a slightly better thing we can do is the following. So we can show that the S color size Ramsey number is bounded below by 1/k. Basically, we can replace this S plus 1 with a different size Ramsey number, a size Ramsey number of a fixed length tight pad. So how does that work? Well, the basic idea behind this thing is, remember here what we did was you separate off low degree vertices, and then you show that you can color these so as not to hook up any pads, right? So the idea here is that if you have some tight path, if you have 2 tight pads and you wanted to connect them up via some vertex, then which edges would you end up seeing? You'd see something like this, and then you'd see this edge and this edge, which means in the link graph of this vertex, you must see a P4 in this example that I'm drawing here. So basically, if you want to use a vertex to connect up two paths, then you have to see a certain lower uniformity path in its link graph. And so basically, what we know is that if a vertex has degree less than the size Ramsey number of that lower uniformity thing, then I should be able to two-color the edges incident to that vertex in a way that avoids seeing that particular structure there. However, unlike in the previous, in this argument, we had enough colors so that I could basically color those, the edges incident to these vertices in L independently and avoid hooking up long paths. Here, I can't do that because the number of colors might be much less than this. So I have to kind of order the vertices in a special way and then color them. But it is possible. So basically, this gives you lower bounds in terms of a smaller uniformity and fixed length path size Ramsey number. So what are some consequences of it? Oh, and by the way, there's a known lower bound on the S color K uniform type paths of essentially S minus 1 plus K over K N. So we can use these things together to prove a couple of things. So when K equals 2 and S is large, I guess this hadn't been studied, but the S color size Ramsey number of P4 is, well, it's upper bounded by the S color size Ramsey number, the S color Ramsey number choose 2, which is basically like S squared, but you can also get a lower bound of S squared by some other argument. So, well, why would I want to look at that? Well, that's the smallest case where I could kind of use it in this bound that we proved up here, right? Because when K equals 3, this says P24, which is just a P4, right? So what does that give us? Well, if I just plug everything into here, I essentially get a lower bound on the S color size Ramsey number of 3 uniform type paths to be this thing, 1/3 S squared, which is essentially like, you know, S cubed N, at least S cubed N. So the dependence on the number of colors is at least S cubed, which, okay, if you compare that to the behavior for the ordinary size Ramsey numbers in S colors, as I mentioned before, it's known to be at most S squared log S times N. So something does change as you increase uniformity. The behavior on S changes, which I don't know, maybe that's not that surprising, but it wasn't immediately obvious that something like that would happen. So, right. And then another thing you can get out of this is basically if you just plug in K equals 3 and S equals 2, it happens to slightly improve this 3 uniform result. Since the size Ramsey number of P4, the 2 color size Ramsey number of P4 is exactly known to be 7, you plug these numbers in and you get a slight improvement over it. But that's not that. So basically, what I want to say is that bounds for general N, it's got kind of an interesting result just because bounds for general N can follow from bounds on this S color size Ramsey number of a fixed length. So like this is the first tight hypergraph tight path that has 2 disjoint edges, right? If you have 2 K vertices and you're looking at a tight hypergraph path, this is the first, like, you know, PK 2K minus 1 doesn't have 2 disjoint edges. So maybe they're, you know, this might be an interesting case because of that. So in particular, if you could show that this thing was at least s to the k for all k, then you would have the lower bound s to the k plus 1 times n for all k. And we know this for k equals 2 now. And we also know that this quantity here is at most s is big O of s to the k. So I mean, the best you could hope to prove is at least s to the k here. And another thing that using that result, if you could prove that the two-color size Ramsey number of pk, 2k, is much bigger than k log k, then you would get an improvement on Winter's result, this log k times n. So that might be something to look at. All right. So the last topic I want to mention really quickly in the last couple of minutes is a different type of problem. So this is back to graphs now. Let me give a definition. So suppose H is a graph and F is a family of graphs. We say that G arrows HF if every two coloring of the edges contains a blue copy of H or a red copy of some F in the family. Okay. So then, of course, the size Ramsey number is defined as the smallest m for which there exists a graph with m edges, such that G arrows H. So the family that we're going to look at here, I guess, when you set that family to be the family of all cycles, then you can think of this property, or, well, you can think of it as HC or PNC for our purposes. This property is the same as G contains a PN even after the deletion of any acyclic subgraph. So you could think of it as, you know, you have an adversary who can delete any forest, a spanning forest from your graph, and you want the graph G to have the property that no matter what forest they delete, you still have a long path. That's essentially what the property G arrows PNC means. So, and then you want G to have as, you know, the smallest number of edges possible with that property. So you want like the sparsest graph, which is, which can still contains a long path after the deletion of any forest. So Dudek, Pralat, and Koini consider this when H is Pn and F is either the family of all cycles, as I was mentioning, or they also consider the family of cycles of length less than Cn. Okay. So what does monotonicity give you here? Basically, if you consider the cycles of length less than Cn, then, you know, as it kind of goes like this, the shorter the cycles that you forbid are, then those provide, yeah, right. But essentially, I'm going to be talking about this. So what they were able to prove is that this size Ramsey number of Pn versus these families of cycles is at most, well, this given thing. So how does this look? Well, as they forbid shorter and shorter cycles, the bound here gets worse and worse, right? So as C approaches 0, this approaches infinity. And then for the family of all cycles, they have an upper bound of 31n. So their idea for the upper bound was just like in the Pn versus Pn case, they used a random graph. A random graph is the construction that they use. But what we showed was that you can get a big improvement over this, over 31n. You can get it down to below 4 by using a completely different type of graph, which seems maybe obvious in retrospect, but basically you want a graph that has lots of long pads, and if you try and split up the long pads, then you're going to delete a cycle, essentially. So we use the cube of a path, and I mean, this has the property that if you try and split, if you delete any tree from this or any forest from this graph, then some path still remains through here, can cut up through here, right? And it, as far as we can tell, like the forest that you can remove, which breaks this, which removes the most number of vertices is something that looks like this. But I think it was just kind of interesting because it was an upper bound on one of these size Ramsey things that used a deterministic structured graph instead of a random graph and did it better. So I think that there could be something there. So I'll just finish up here, mention a couple of open problems. Well, closing the gap on the size Ramsey number of Pn would be interesting. I think that this S color version for pads, removing this log S factor if possible, if that's the truth, would be good. This thing I mentioned earlier for hypergraphs, if you could understand this S color size Ramsey number of this 2K vertex K uniform type pad, then you would get a general lower bound on the S color K uniform type pads for N. You would know something about the dependence on the number of colors. So, all right, that's all I wanted to say. Thank you for listening.
Thanks, Deepak. Maybe we could unmute and give him a round of applause.